my name is Nikita, and this year I investigated the evaluation of neutron generator stability using copper fault activation, gamma ray spectroscopy, and also neutron detection. The current method in order to analyze soil is an ex situ method, where the samples have to be taken out of the forest soils and into the lab setting. So the extent of this approach is very limited, and it's inadequate for a quantitative determination of carbon and other elements which we're trying to sequester. So the carbon levels over a large area by this new method called INS, which is inelastic neutron scattering, is an in situ non-destructive method, and it will monitor carbon sequestration and other elements such as nitrogen and phosphorus. So this multi-elemental technique is used to analyze the components that are found presently in the soil. So in order to process the sample, the INS system uses the acquisition of prompt and delayed gamma rays from the neutron output from the spectra. So the neutrons are produced by a radioactive reaction, where you have deuterium and tritium combining to form 14 megaelectron volts, which are shot into the sample. So the neutrons then interact with the soil, and the amount of gamma rays that are detected afterwards coordinate to which element of the specific gamma rays that are found presently in the soil. So for the pulse neutron generator, which is what I used for my experiment, there's two optimal gates, where you have the inelastic neutron scattering gate and the thermal neutron capture. So the inelastic neutron scattering gate, also referred to as INS gate, is when you have the neutrons actively being shot into the sample. For the thermal neutron capture, that's when the neutrons are not actively being shot into the sample, but that's when there's the delayed capture of elements that take longer to irradiate. So during the different duty cycles of which I tested, there are variations in the pulses that are caused by active and inactive timings of cycles where the neutrons are not always being emitted. So the gamma ray energies are then monitored by a detector and are shown in a histogram. So the nuclear reaction is examined, demonstrates the proportional value that the element that is found in the sample. So these are the two types of decays that an element can undergo, either alpha or beta decay. Alpha decay has two releases of gamma rays, and beta decay having one release from the excited to its ground state. So in order to test the neutron generator stability, what I had to do was copper foils were placed onto an acrylic plate and inserted underneath the neutron generator at 11 3/4, right below the neutron generator. Below that, we had a carbon sample, which was approximately 11 3/4 inches below. And what would happen is that the foil and the carbon sample would be bombarded with the neutrons that were being produced from the generator. So it was monitored using a DNC software, which is called the Delayed Neutron Counting Software. So the radiation would last for about 20 minutes under different cycles of 2, 3, 4, and 25 and 20 minutes. So in addition, the radiation would be repeated under the various frequencies which I tested, which was 1,000, 5,000, 10,000, and 20,000. So the neutron count and gamma ray spectroscopy for the inelastic neutrons were taken with these two machinery shown here, this being the neutron detector and this being the gamma ray detector. So that was monitored using a different software called eMorpho. The copper foils were then removed after the 20 minutes had elapsed and placed into a scintillating detector, where the electrons that are being released from the copper foils would be amplified, and we can quantitatively assess the peaks that you would see from the electrons in kiloelectron volts that were measured. So what I found in the copper foil activation was that there was a lot of instability and fluctuations, where between the three trials, I normalized the values at 10,000 at 25%. That being an error in my procedure where the 20,000 at 25%, which was the highest part of my experimentation, they would sometimes reach the beam current, and then the machinery would time out and wouldn't be able to fully use those trials. So at 10,000 at 25%, it was the second longest duration of time that the neutron generator would be on. So I normalized it to that value, and that served as a comparison point. Between all the trials, I experienced fluctuations between 11 and 47%. In addition to that, another part of my project was gamma ray spectroscopy, and that was analyzing the silicon peak. So for the INS and TNC, I had analyzed silicon, and that was another source of error in my project, because originally I was trying to monitor carbon, but as a result of the amount of silicon found presently in the sand around my experimental area, it showed a stronger peak in my results. So that served as across all the trials, I was able to choose that one element as my comparison point to evaluate how stable the neutron generator was. So I again compared it to the 10,000 at 25%, and what I saw in the fluctuations here was between 13 and 11%. So for the neutron summation, that is to show that the neutron detection actually is occurring. So neutrons are actually being actively submitted into the soil. So I again normalized it to 10,000 and 25%, serving as a comparison point. So in addition to this project, what I want to do in the future is to investigate the data and see why these fluctuations were happening. In addition to that, this INS technology will be very valuable in the future, where they can be used to examine forest soils and help to understand carbon sequestration, and it could also help to form policies. In the future, based on the further analysis of this data, what I also want to do is look at neutrons generated per pulse. When it's generated per pulse, what I also want to look at is the delayed and extension period. The delayed period being 7 microseconds and the extension period being 3 microseconds, where I'm looking to find the optimal time to actually look at the gamma rays that are being collected. So in addition to that, I want to look at different elements such as carbon, oxygen, and silicon, and actually see how they have different effects from the neutron generator.